All right, let's see. Reminder that you have your quiz tomorrow. All right, let's go over this guy. Where is my pen? All right, I'm going to have you guys stop working in your groups. And I'm going to have you guys look up here. Let's go over it piece by piece. Yes, when you read the question, it looks like it's a very simple question because we did tangent lines way back when and normal lines. But the derivative is involved and it involves trig. So I'm trying to make sure you understand how important it is that you know your trig problems or your unit circle because it is going to show up over and over and over again. These are the common types of derivatives that you're going to see on the AP. They all will have rules, a minimum of 1. So this one has 2. It has 2 chain rules. So what do I tell you guys to do when you start out your problem? No, I don't say take a derivative. Rewrite it. All right. Some of you skip that step. If you skip it and you get your derivative right every single time, I'm fine with that. But many of you skip it and keep getting it wrong. So stop skipping the step. It helps. So I can tell that this is going to be the inside of my function. But I can also see that there's another inside. That's how I know that there's 2 chain rules. On top of that, just by looking at that inside, because you always take a derivative of in, I know that I'm going to have a 2 sitting in my answer. Okay? Those things are helpful. So if you know it's not sitting there, something went wrong. All right, let's do our 3 steps for our derivative. All right. Step 1. Noah. I know you guys are discussing something important. I do know that. But I am going to interrupt you to ask you, what's the first step of chain rule? Take the derivative of? Thank you. I want it in words so that any problem you do always is the same. So that's my outside function. There it is. And then, Ariel, what do I do with the inside? Leave it exactly the same. All right, there's my inside sitting right there. Anthony, what do I do at the end here? So I'm going to take the derivative of the inside, but what do you notice about the inside? It's another chain rule. So I'm going to put a big old box here just so you know that this whole thing is my dn. All right, so here we go one more time. We're going to do another chain rule. Timon, and now I got to do the derivative of the outside, and what is that? So that's my derivative of the outside. Nathan, what do I do with the inside here? Leave it. So there's my insides. And then Danny, what do I have to do at the end? Derivative of the inside, which is 2. So there's every single piece, each part done. Okay, you want to follow that process. All right, then you guys probably simplified this and got -6 cosecant, turns cubed again, just like we started with, cotangent. All right, so I like simplifying just so that I have less to do later. That's all. Okay, so and actually because I'm going to calculate with it. I'm even going to leave it like undo. I'm actually going to leave it like this. All right, so then you guys figured out you're going to have to substitute in the pi over 3. And when you do that, what are your angles each time? 2 pi over 3. So let's come over here and let's draw our unit circle. 2 pi over 3 would be here. What's the point at 2 pi over 3? This is the argument I kept hearing. -1/2 is correct, comma, square root of 3 over 2. It is cosine, comma, sine. Hold on. So I get -6. So the cosecant of 2x, which would be the cosecant of 2 pi over 3. Cosecant is the reciprocal of which function? Sine. So sine is your y value. So I'm going to reciprocal this guy. All right. So we get 2 over root 3 cubed. Is anyone lost so far? Alrighty. So cotangent, I always do the same way. Let's see. Ellen, do you remember cotangent is equal to a fraction? Do you remember what the rule is? Involving sines and cosines. Is actually correct. Alright, so cotangent is cosine of theta over sine of theta. So that means for this part right here, cotangent of 2x, I can take the cosine value, negative 1/2, divided by root 3 over 2, which is multiplied by the reciprocal. These will cancel, and you end up with negative 1 over root 3. I want you to check your papers right now because I saw a lot of wrong answers for those two pieces. All right, so now I need a physical number answer. So negative 6 times a negative, those will be positive. 2 cubed is how much? 8. All right, so root 3 cubed, but then I'm going to multiply by another root 3. So root 3 times root 3 times root 3 times root 3. Okay, that's what it means to go to the 4th power. What is that value? It is 9. Okay, so like I said, it does simplify a lot. This would be 2, this would be 3. Oh, 16 is what I'm supposed to be writing. 16 over 3. All right, so I need someone to tell me what I just found in words that make sense. Annie, what do you say? The slope of the tangent line. Beautiful. And you're finding it exactly at a place. Okay? At pi over 3. Perfect. So how is that helpful? David Soriano, how is that helpful? All right, so I'm going to need the normal line slope. What is the normal line slope? Ooh, I just want the slope from here. 3 over 16, is that correct? Negative. It's negative. Why, Laura? Is it negative? It is the negative reciprocal, or I also say the opposite reciprocal. So don't forget about that little opposite, because this answer will be there without the negative. All right, so this is my slope of my normal line, which is the perpendicular of my tangent line. Are we good so far? Now, we're halfway there. We're more than halfway there. So we got y prime of pi over 3 is negative, was it 3 over 16? Okay. Y of pi over 3 would be cosecant of 2x whole thing cubed. But didn't we already find the cosecant of 2x? Yes. How much was that value? 2 over the square root of 3. Thank you so much. All right. And then that whole thing cubed, which gives me 8 over 3 square root of 3. All right. So what is our final answer? Y minus the y of the point equals the slope times x minus the x of the point. If they ask you to find the slope of the tangent line at a place or the slope of the normal line, this better be a physical value. A lot of you keep putting the derivative in here and leaving that, and I don't know why, because I've never shown you that in my life. We have never once done that in this class. It should be a physical value because they want to know the slope of the tangent at a point. Yes? I don't know. Okay. Write it down. You missed something. Lottie, put your head up. All the way before I email your mother this video of me blasting you in class. All right. Okay. So, we good? No other questions? You're good with that question? Joshua, did you answer the question for yourself? It can be, but I just simplified it. Okay. All right, so that was just a little review. Wanted to make sure that the trig values are not gone, that you can still do your derivatives. And yes, something like that, other than the normal line stuff, can be on the quiz for tomorrow. You have to be able to combine rules. Okay? All right, so let's look at section 6.1, day 2, which is slope fields. Slope fields are kind of cool because they're easy. And looking at a real slope field, and I have not defined a slope field, here's my definition. It is a field of slopes. Ta-da! So it is literally take a coordinate axis and just draw a bunch of mini little tangent lines. And the crazy thing is, when you draw your mini little tangent lines, it's going to start looking like a function. It's really odd that it happens, but it's a nice thing that happens. All right, so I'm actually going to skip that. We don't really need to do that. I do want to go over one homework question before I get there, because every year when you do your homework, this specific homework, I get the same question, 21 to 24. And I purposely do not teach 21 to 24 because you already know how to do 21 to 24. It said use FTC. It is not hard at all. So I'm going to actually take number 21, I think. It gave you y of 1 equals 5. It gave you that dy dx is equal to sine of x squared. And I'm actually going to restate the question. I'm going to say, without evaluating it, I'm going to say, well, let's actually call this the velocity. Let's call this the position. Okay? And I want you to find the position at a new number, 100. All right, so let's do the question. So I have, here's my question. You go back to what's given. How do I go from velocity to position? Antiderivative. All right, so that much makes sense. But we remember that if I want a final position, what do I also need? An initial position. Look at that. And if I have an initial position, what has to go here? The exact same value up to. Okay, so what does this say so that you understand what integrals mean a little bit better? If I want to find the final position, I need the original position plus the change in physical position is what this integral does. Change in, which is why so many of you keep getting the question wrong when I ask, oh, what's the position at 100? And you just give me the integral. The integral gives you the change in. Remember that thing I keep saying? If I tell you I changed in age by 10 years, is that enough to tell me how old I am? No, it is not, okay? So, given that, how would I change it so I can find the position anywhere? I want this to be an x. So what changes? So 1 to x. There's your answer. So going back to the original notation. And so, yeah, because of FTC in a sense. It can't use the same value. So, change it. Yeah, this should be a dummy variable. Pick a letter. You don't want to use x and then call this also x, which is why now I'm just changing it to t. I could change it to any variable that I choose. Okay? Good? All right. You see the analogy? So it's literally FTC. I'm going to show you the one other thing. Because it said don't evaluate, just said use FTC. Your answer is going to have a definite integral. I thought there were enough little tips to try to get you through. So remember that the integral from a to b of f of x dx is equal to big F of b minus big F of a. So without knowing all of what I just did a second ago, I really could just solve for f of b is equal to, move that over. You see how it looks exactly the same as what we just did a second ago? Yes, I showed that to you. Yes, it's in your notes. It's the other way to look at FTC. Okay, so that's the other way. Because then I showed you this and then did a position problem so you understood what this integral actually meant. So let's say you take this integral and the units are degrees. Then this is the change in degrees from a to b. That's how you use your units to always. So integrals are always a change in every single time. Okay? All right. So is that pretty much the only question from homework that you probably had? Is that accurate? Okay. All right. So we're going to do slope fields. Slope fields are easy, as long as your mental math doesn't go awry. So here's what a slope field is. It essentially gives you this graph, this coordinate axis, and says, draw a bunch of tangent lines on here using the equation of the derivative. So you don't know anything else. You don't know what the function is, but you just know that the derivative is 2 in this case. So I'm going to pick a point. I pick 0, 0. Okay? If I substitute 0, 0 into my derivative, how much will my slope be? 2. It's not a trick question. It is a constant, so it's 2. So how did I draw that little tangent line? You're going to imagine this whole entire line because that's a rise of 2 over 1. So that's what it would look like. You're only going to draw a tiny, tiny little piece of it. Okay? So how do I check for accuracy? I look and see that if everything is 2, then they all look kind of parallel. If it's supposed to be positive, it looks positive. If it's supposed to be 0, it looks like 0. I will not be able to tell the difference between a slope of 2 and a slope of like 2.5. Okay, I can't tell the difference. Or even maybe the slope of 3 sometimes even looks a little hard to see. Okay, so accuracy is a little difficult. You just want to make sure if it's positive, it's positive. If 2, say the next slope was 3, then the 3 slope should be steeper. That's essentially what I look at. All right, in this case, any other point I pick, how much will the slope be? 2. So that makes this easier. We're not going to go all the way to the edges. I will tell you that if you have an AP problem where you have to draw a slope field, they always make you do 12 points. Okay, this is way more than 12 points. Okay, but generally speaking, if there were a bunch of these, you would be able to kind of see what the original curve looks like. And I'll show you that it does become better and better. Now, my question is, I did a slope field, and I'm going to do the same as the other class. I did 25 points. All those points are within this yellow square. I did 25 slopes. How many points are in the yellow square? Bah. It's my wrong noise. Bah. How many points are in my yellow box? I did 25. How many points are in my yellow box? An infinite amount. Did I do a slope at every single point possible? No. You have to keep that in mind. These are not all of them. Just a sum of them. Okay? So please keep in mind that there are just 25 points. It's an infinite amount of points in there. And if you wanted a more accurate slope field, you would do more points. Okay? All right, so let's do number 2. Number 2, I pick 0, 0. How much is my slope? 0. Did I just hear 1? 0, comma 1. How much is my slope? That says X, FYI, and I said this point. Okay, there we go. So X, when I say 2 numbers, which one's going to be the X? The first one. Let's keep that in mind while you yell out numbers. So 0, comma 2. Still 0. Look at that. 0, comma negative 1. 0. You see a pattern? All right. X equal to 1, y equal to 0. How much is my slope? 1. All right. 1, comma 2. 1, yell them out for me. 1, comma 2. 1. All right. And then 1, comma negative 1. All right. 1, comma negative 2. 1. All right. Then we go to 2. 2, comma 0. Hello? 2. Please give me serious answers. 2, comma 1. 2, comma 2. 2. You see a pattern? So follow it. That way you don't spend too much time on it. All right? What about negative 1? Negative 1, comma 0 would be negative 1. Negative 1, comma 1 would still be negative 1. Negative 1, comma, and so on. All right. And then negative 2, comma negative 2. Negative 2. And then you should realize that all the points when x is negative 2 will have a slope of negative 2. Can you kind of see the shape? It's not a perfect one, but you start to see. You guys know that if we took the antiderivative of x, it's 1/2 x squared. This starts to look kind of like it. Not perfect, but you do see the shape. Now, if you think about if you had a computer that could build literally a huge coordinate grid where they found the slope at increments of 0.01, then your slope field is going to look way better than ours, okay? All right, last one. And then we're going to fill out the little table guy down here. Last guy, 1/4 x squared. Once they start putting in functions, it takes a little bit longer to do. Just please don't make a calculation error in your head. All right? So I'm going to pick the point 0, 0. If I substitute that in, what do we get? 0. How about 0, 1? Okay, let's follow the pattern. We understand that that's going to happen. All right, 1, comma 0. 1/4. So how do I do 1/4? Rise 1 over 1, 2, 3, 4. So if I kind of draw that very not steep line, How about 1 comma 1? 1/4. So I'm going to draw that not so steep line, and I'll do it all for my x equal to 1, and then I'm going to go over to x equal to -1. What happens if I do x equal to -1? Oh, be careful. X equal to -1? It's still 1/4, because what happens to your x values? They're squared. So they're going to look exactly the same at x equal to -1. Now I'm not going to do 2 and -2. Okay? You could if I asked you to continue. I'm not going to do all of them. What's actually really important is understanding the bottom. So the first one's easy because they're all 2. So we know that you'll never have negative slopes. You'll never have 0 slopes. You'll never have undefined slopes. And you get that the slopes are greater than 0 always for every single. So when x is all real numbers or y is all real numbers, for any of them you'll always get that the slope is positive. So now we get into here. Now it's a little different. Okay? Is there a way to make the function x undefined? The only way you can undefine functions, or have undefined functions, x in the denominator of a fraction, ln function, log function, even roots. Any issues? No. All right. Can we make it 0? Is it possible to make that function 0? Yes, when x equals 0. All right. What about making this guy positive? When x is greater than 0. Okay. And what about negative? X is less than 0. Beautiful. Pretty easy. All right, let's do this guy over here to the right. Is there a way to do this undefined? Get that slope to be undefined. Notice where I always start. I like to start here. And then is it possible to make it 0? Yes, we see them on the graph at x equal to 0. Is it possible to ever have it be negative? No. You should realize that. Never, never, never. Doesn't matter. And then when will it be positive? When x is not equal 0. Beautiful. Okay? Beautiful. All right, so now these derivatives look a little funny because now they have y in them. But the concept is essentially exactly the same. Pick a point. 0, 0. Substitute that in, and what do you get? 0. How if I go up to 0, comma 1? What's my slope now? 1. I was hoping it would be 0. How would I make them be 0? The x value, change the x value. All right, 1, comma 0. What's my slope? 0. Good. So yes, if I change my x value but keep the y value, what specific value? 0. All right. And then, oh, same color. Let's keep that color. How about if I go to 1, comma 1? It's 1. 2, comma 1. It's 1. Negative 1, comma 1. It's 1. You see the pattern? All right. What about negative 1? All the y equals to negative 1 would be negative 1. So once you figure out the pattern, it makes it go a lot quicker. We're not going to fill out the rest of that. Okay, doesn't need to be perfect. And then let's look at number 5 here. So, when or is it possible for me to make the derivative undefined? Never. Is it possible for me to make the derivative equal to 0? When y equals 0. Beautiful. Is it possible for me to make the derivative positive? Y is greater than 0, and then easy, y is less than 0. I'm going to skip number 4 just because it's very similar to what we did for x. Yes, sir. Isn't that a cusp? Not necessarily. Not necessarily. It isn't. You'll learn in 6.4 what the actual function is and how to know, but no. It's really hard to see the exact function, especially with that limited view of the slope field. But you're actually going to find the antiderivative of that function, and no, it is not a cusp. Okay? All right, so let's go to number 5. Oh, I totally didn't change that number to a 6. All right, 5 and 6. So these now combine your x's and y's. It's just to show you the sequence, because once you start combining, it's a little bit more mental math. That's it. okay? I just want you to be careful when doing those problems. All right, so I'm picking the point. 0, 0. Say that one more time. 0, 0. Undefined, why? You can't divide by 0. You guys know that. Why did I hear half of you say 0 then? All right, so we know that it's undefined. Then you're not going to draw a tangent line there. If you want to put a little point just to say you did that one, you can, but you don't draw a tangent line. What are the undefined derivatives? There's 4 different ways to get them, which is why you can't draw anything there. What are the 4 ways? Vertical tangent, a corner, a cusp, and a discontinuity. We don't know what's happening there, therefore we can't draw anything there. Does that make sense? Okay. All right. Secondly, let's pick another point. 0, 1. 1. Be careful. 0. Is that right? I think that's what I heard. 0, 1 is what I said. I would hope it's 0. Oh no, I'm just taking what you guys tell me. It is 0. I'm writing up what you tell me because I would assume that you guys can take that fraction and make the value. All right, so let's pick 1, 0. Undefined. Undefined is correct. All right. Should notice a pattern. 2, 0. Undefined. -1, 0. -2, 0. All right. Let's try 1, 1. 1. 1, 2. 1, 2. 1/4 would be the number I'm looking for. So you see how your mind's just messing up the simple calculations? Then write the calculation down. You know, don't do it in your head. Don't risk getting it wrong just because you don't feel like writing it down. So 1/4. All right. Let's do 1, -1. 1, -1. 1, -1. Write it down. I'm getting half of you giving me wrong answers, so write it down. I don't know. You gave me 1/4. Oh, I did put it in the wrong place. That one I do know. That one I did not mean to make a mistake on. Is it? You told me 2, 1. Okay. Okay. So, therefore, thank you. I was wondering how long it would take. Alright, so how much was that one? 2 is correct. Every time I do it, I always get wrong answers because you think you're just, let's just quickly do them, and you mess it up in your head. So the point of this is I understand the calculations are easy. Write it down. Write it down so you don't get them wrong. You don't want to waste a point just because you mentally calculated something that's very basic really incorrectly. All right. 2, -1. 2 is correct. All right, let's go over this way. 0, -1. Okay. -1, -1. -1, -1 is what I said. I don't know why we're not writing it down. So it's -1. So write it down. Stop skipping that step. -1, 0. Undefined. -1, -1. -1. All right. -1, -2. It is -1/4. So down 1 to the right 4. So it's very not steep. All right. I don't really care how many you do there. I just wanted to go through the calculations. When they start mixing the x and y, right there, you're taking the x value, you're taking the y value, you're doing something to it and then dividing it. Your mind, especially when you do a lot of them, it just kind of loses its place. That's what's happening. That's why you're getting it wrong. Not because you don't know how to divide two numbers. You're just losing your place. So write it down if you need. Just quickly write them down so you see them. Okay? All right. With just that much done, we can actually answer these. Where did I start every single one of these? On the undefined. I think it's the easiest place to start, and I actually start with undefined, go to 0, just like a sign chart. I do it just like a sign chart. So, I do my slope undefined. Is it possible to have an undefined slope? Yes. Where did we get those? When y is 0. So double check. When y was 0, which would be here, I have no slopes, which is correct. All right. Can I make the slope be 0? Yes. Where? When x equals 0. And when y does not equal 0. You need that. You have to have that. Because if you do just this, it means y is allowed to be anything I want it to be, and I want to pick 0 then. And then that would make this statement false, so you need the y cannot equal to 0. Okay? Are we good on that? All right. So now I come up here and I say to myself, well, if I'm going to do these two, I look at the function and I see if there's anything that would help me simplify the process. And squareds, even powers, even roots help simplify the process. Why? Whenever I put a number into the square root or the fourth root or a square or a fourth power, what always results? Positive or, not negative, positive or 0. Those are the only values you can get. We already did our zeros, so I know that if I'm looking for positive and negative, is my y squared going to help me at all? No, because it's always just going to be positive. I get to do this whole problem just using x now. So how can I, just looking at x, make my derivative positive? When x is greater than 0. How about negative? But be careful. What do I have to add in? And y cannot equal 0. And y cannot equal 0. You have to have the and. Because if you don't put a y statement, it means y is allowed to be everything, which was okay before. Look here. We didn't put anything extra because I'm allowed to use y be everything. Y can be anything here, y can be anything here, y can be anything there. Okay? Are we good? All right. Thank you.